A matrix is an array of elements. You can even be more specific than this. It's a rectangular array of elements. Has m number of rows, n number of columns. Together, m by n refers to the dimensions. Okay. What I'm doing here was drawing what would be then a generic version of some kind of a matrix where all of the elements are A. This would usually be then referred to as matrix A with a capital A. All the elements are little baby A's. And each element is identified by two numbers that identify its position. The first one is the row, and the second one is the column. And generically, if you're referring to any one in between, it's A, I, J. So if I said to you, what row is that in? You would say it's in the fourth row. And if I asked you what column it's in, you would say it's in column 7, right? That's all that is. All right. So the first thing we need to learn are matrix operations. Okay. We talked about one of the most difficult ones yesterday. I started out by diving in. We could talk first about addition and subtraction. So let's do that. If we take matrix A and add it to matrix B, no matter how big they are, the one thing you have to know is that they have the same dimension. They both have to have the same dimensions. Because what you're going to do in order to add or subtract them is take each element of the first one and add it or subtract it to an element of the second one. So that would become your first element. You would go all the way out for as far as you had to go. You would go all the way down for as far as you had to go. And again, this is why we like to have ways to write things generically. Okay. That's how you find each element of the added or subtracted matrix. You take each corresponding element and add it or subtract it. Then there's something called scalar multiplication. And it's called scalar multiplication because we're really talking about putting something to scale, making it larger or smaller consistently all the way through. How do you do that? Well, if I have matrix A and I want to change the scale of it, it means I'm going to take some constant C, not a matrix, but a scalar number, one of the regular numbers. Each element, A, I, J, is just multiplied by C. Multiplication, matrix multiplication, right? Matrix product. Okay? So now we're talking about A, B. This one's more complicated. This is the thing that we talked about yesterday where we had the pizzas. Right? We had lunch and dinner. And we had pizza type 1, or let's call it pizza type A, pizza type B, pizza type C, pizza type D. And there was a matrix here that represented how many were sold. And then we had another matrix that represented how much each one was sold for. And in order to find out how much we made, how much revenue did we have, we multiplied these two matrices together. So if we're just talking about lunchtime pizzas, how much did we make? How much did we bring in at lunchtime? We would multiply how many of the first pizza we sold times how much we sold it for. how many of the second pizza we sold and multiply it by how much we sold it for. Multiply how many of the third pizza we sold and multiply it by how much we sold it for. And one more time. And we would take all of that and add it up, and that would be the first element of our matrix. So let's see, can I write that generically here? So what would we do for the second row? For the second row, I would take A, 2J, and multiply it by B. This would be B. See if we can do this right. A, 2J, that would be every element of A in the second row and every element of B in the second column, and add them together for each I equals J equals 1, right, through whatever we got. Have you guys seen that notation before? The summation notation? Yes? Okay. It just means add them all up. And you'll notice that in each one of these situations, the column number of the A equals the row number of the B, and it's got to work out. In other words, there's got to be 1 for 1. If I had too many prices over here, or if I had a fifth kind of pizza without a fifth price, you would come back to me and say, I can't figure this out. What are you talking about? That means that this is only possible if the dimensions of A are equal to, let's just call it m by n, right? They could be anything. And then the dimensions of B has to be n by p. When we go to do this multiplication, we're going to multiply each member of the column in the first one times its corresponding member in the row of the second one. Now, keep in mind that means this is not commutative, and that means a reasonable question on a test would be to ask you to add or subtract two matrices or multiply two matrices, and one of the possible answers could be can't do that, does not exist. Okay? Okay. So in other words, A plus B might not exist, and A times B might not exist. Now, yesterday for homework, the thing that I left you with at the end of class was this down here. Right? The question was, right? The question was, if we had A times B and then times C, would that be equal to A times B times C? Would the associative property work here? And in this case, in case you did do it later at home, this one times this was equal to 1044, and A times the product of BC came out also to be 10 over 44. So these were equal. But now, with all of the information that I just gave you, it should be pretty straightforward to answer these questions. First of all, the first one was, what is a matrix? And we just said it's a rectangular array of elements. The dimensions of the matrix, where is the matrix? At right. Okay. So the number of rows by the number of columns, this would be 4 by 2. What is the element in row 3, comma 2? Well, 1, 2, 3, 2. That would be 85. If Aij represents the element in row I and column J, what is A21? That would be 458. What does the sum of elements in each row represent? Yeah?
I said number of people.
Right, it's the number of members of Congress. These are the 107th, 108th, 109th, 110th Congress. All they did was split it into male and female. There are 435 members of Congress. So in each one of those rows, it adds up to 435. And that's why.